Hello students, welcome to my lecture on operating system. Today I will discuss the round robin and multi-level queue scheduling algorithm. I am Shravani Kundu, Assistant Professor, Department of Computer Science and Engineering, Guru Nanak Institute of Technology. After going through this lecture, you will be able to solve any numerical problem based on the round robin and multi-level queue scheduling algorithm, and you will be able to understand why we need the multi-level queue scheduling algorithm. So now, first I will discuss round robin scheduling algorithm. This round robin scheduling algorithm is basically required for a system which works on the time sharing basis. That means round robin scheduling algorithm is specially designed for time sharing operating system. The basic working principle for the round robin scheduling algorithm is same as FCFS algorithm. So that is first come first served scheduling algorithm. So basically it works as per the FCFS algorithm, but along with this FCFS algorithm we added the preemptive nature. That means we added the preemption plus some time quantum. So based on those, by using those all the three features, we can design the round robin scheduling algorithm. Now, what is the nature of this algorithm? For this round robin scheduling algorithm, there is a time quantum. Let us say that capital T is that time quantum. Now, in that time quantum, some time unit is assigned to them. For example, let us say the time quantum is 2 milliseconds. So what happened in that case? When a process or a set of processes will be present inside the ready queue, then the scheduler select the first process which is inserted in the ready queue. That is based on the FCFS scheduling algorithm. Now, so for example, let us say this is my ready state and ready queue is associated with it, and inside the ready queue there are two processes P1 and P2. Now P1 is inserted first and then P2. So scheduler will select P1 first and that P1 will be assigned to the running state for the execution. Fine. Now the P1 will execute how long? It will execute for this 2 milliseconds. That means for the time unit which is specified in the time quantum. So P1 will be executed by the CPU for 2 milliseconds. After 2 milliseconds, P1 will leave the CPU by itself and it will come back to the ready queue. That means after 2 milliseconds, the execution of the process P1 will be forcefully terminated, stopped, paused, and P1 will be sent back to the ready queue. And then P2 will be selected and again it will be assigned to the running state for the execution. Again, after 2 milliseconds, after the completion of the 2 milliseconds, the P2 will again come back and it will be stored inside the ready queue, and as there is no other processes, so P1 will again get the chance for the execution and P1 will be assigned to the running state for the execution. So what we can see over here, based on some value of the time quantum, the processes which are present inside the ready queue, all the processes will get chance for a specific time duration for the execution. That means when the process will be assigned to the CPU for the execution, it will execute for a specific time duration, and after that time duration, it will again come back and it will be stored inside the ready queue. Okay. Now, if the duration of the process, that means the execution time of the process is less than the time quantum, in that case the process will stop, complete its execution within that time, and it will be shifted, it will change its state from running state to terminate state. Fine. So there is the state terminate. So a process will change its state from running state to the terminate state when it completes its execution during this time quantum. And when the process will switch from the running state to terminate state, then another process which is waiting in the ready queue will be selected and will be assigned to the CPU for the execution. So that is the overall process for the round robin scheduling algorithm. Fine. So now we will discuss a problem on the round robin scheduling algorithm. Consider the problem which is given over here. There is a set of processes P1, P2, P3, and their burst times are given as 24, let us say it is 24 millisecond, 3 millisecond, and 3 millisecond. Now we will execute those problems using those set of processes using the round robin scheduling algorithm. And before that, we need to know about the time quantum. So let us say the time quantum for our system is 2 millisecond. Fine. So we will draw the execution pattern with the help of the NAT chart. So P1, P2, P3, we assume that P1 is inserted first in the ready queue, then P2, then P3. So those are the order of the insertion, order of the presence in the ready queue. So as P1 is inserted in the ready queue first, it will get chance first for the execution. So P1 will start its execution. It will start from 0 and it will execute for 2 milliseconds. After 2 milliseconds, so this duration is 2 milliseconds. After 2 milliseconds, the P1 will leave the CPU and it will go back to the ready state or ready queue. Now, when the P1 will leave the CPU is free, then the scheduler will select the next process, that is P2 for the execution. Now P2 will continue for again 2 units. Now you can observe one thing that after completion of the first 2 units, the remaining burst time for the process P1 is 22. And after completion of the 2 units by P2, the remaining burst time for the P2 is 1 unit. So P2 will continue till 2 units and it will end, that means the next time slot will start from 4. Now, next P3 will be selected from the ready queue and it will be assigned to the CPU for the execution. So P3 will be assigned to the CPU for the execution. Now P3 will start from 4 and again it will execute for 2 units and it will leave the CPU when it is 6. Now again the same scheduling will happen, again it will start from P1. So after completion of the P3, the remaining burst time for the P3 is 1 millisecond. Now the next process is P1. Now P1 has 22 millisecond burst time. So again P1 will start its execution and it will continue for 2 units of time. It will leave the CPU when it is 8. Now after P1, the P2 will start. Now you observe that P2 only has 1 milliseconds burst time. That means, and the total duration of the time slot is 2 milliseconds. So P2 will take only 1 millisecond from that time slot and it will complete over here. So it will leave the CPU at 9. So again, at the time of 9, the next process P3 will start its execution. So P3 will start its execution at this point. And again, as the P3 needs only 1 unit of time, so it will leave the CPU at the time 10. Okay. Now, when the P3 will leave the CPU, so execution of P2 and P2 is completed. So P2 and P3 is no more present in the ready queue. Only P1 is there. So P1 will get chance for the execution. And see, as no other processes are there, So P1 will continue, and it will continue. What is the remaining burst time? So P1 has the remaining burst time 20 unit, because P1 is executed over here for 2 unit and over here for 2 unit. So 4 unit is already executed. For now the remaining burst time is 20 milliseconds. So P1 will start its execution from the 10, and it will continue, and it will leave the CPU when it is 30. Fine. And here you observe, here the time slot is divided into like that: 10, 12, 14, so on. And each time slot the P1 is there. As no other processes are there, so P1 will continue and it will complete its execution. So this type of scheduling is called the round robin scheduling algorithm. Now here we will find out the same thing. We need to find out the average waiting time. So before finding the average waiting time, we have to find out the waiting time for each process. So what we will do? We will find out the waiting time for each processes. So what is the waiting time for the process P1? So you can see P1 started from here, and we assume that all the processes arrived at the time 0. So for this time slot, the waiting time of P1 is 0. Now again, P1 got the CPU when the time duration is 6. So what is its waiting time? Its waiting time is this period. Okay. So what is this period? 6 minus 2. So we have to write 6 minus 2. Now again, P1 has to wait for this unit time period. What is this time period? This is 10 minus 8. So this is the overall execution waiting time for P1. Now next we will compute the waiting time for P2. So P2 start at 2 and it arrived at time 0. So the waiting time is 2 minus 0. Now next, P2 start its execution at this point. So that means its waiting time is from here to here. So it is 8 minus 4. So we have to write 8 minus 4. And thereafter no other P2 has completed its execution at the next slot. That means at the second slot P2 has completed its execution, so no other waiting time is there. Now we will compute the same for P3. For P3, the waiting time is 4 minus 0. Okay. Now, so as it is started from at the time 4 and it arrived at time 0. Now P3 got its next slot at time unit 9. So what is its waiting time? Its waiting time is from this to this. That means this 9 minus 6. So its waiting time will be 9 minus 6. Fine. So we will get the final waiting time, total waiting time. So the total waiting time for P2 is, P1 is 6. Okay, 6 minus 2, 4, and plus 2, 6. For P2, the total waiting time is 2, and this is 4, that is again 6. And for P3, it is 4 and 3, that is 7. Okay. So you can see the total waiting time for P1 is 6, P2 is 6, and P3 is 7. So the average waiting time, we will compute the average waiting time is equals to 6 plus 7 divided by 3. That is the total number of processes. So it will be 19 by 3. So this is the average waiting time for the process. Okay. Clear? Now, if you increase the time slot, that means the time quantum, to some other value, you can see that the average waiting time will also change. So one thing you can conclude over here, that once any process gets the CPU for the execution of the process will be terminated forcefully after the total time of the time quantum gets over. That means here the execution can be forcefully stopped or paused due to some other external affairs. It may be interrupt or something else. So we can say that the round robin scheduling is totally preemptive scheduling algorithm. So what is preemptive scheduling algorithm? In case of preemptive scheduling algorithm, if the execution of a process can be forcefully stopped due to some external event like interrupt or some other existence of some other high priority processes, then the execution of the current process can be forcefully stopped. So this type of execution is called the preemptive execution, or this type of scheduling algorithm is called the preemptive scheduling algorithm. And if the execution of the process cannot be forcefully stopped, then in that case, it is called the non-preemptive scheduling algorithm. Okay. Now next, we will discuss another type of scheduling algorithm, which is called the multi-level queue scheduling algorithm. So in case of multi-level queue scheduling algorithm, as you can see over here, the ready queue, which is associated with the ready state, that ready queue can be divided into multiple sub queue. So far, whatever the scheduling algorithm you learned, in all the scheduling algorithm, the ready queue, which is associated with the ready state. So this is our ready queue. Now, the ready queue has only one level, no other, so only a set of processes can be stored over here. But in case of multi-level queue scheduling algorithm, this ready queue is again divided. So here you can see this is a single ready queue is divided into 1, 2, 3 sub queue. So let us numbering it: queue number, sub queue number 1, sub queue number 2, and sub queue number 3. So this ready queue is basically divided in this way, 3 sub queue. Fine. So this is called the multi-level queue, and the algorithm which will be applied on this multi-level queue is called the multi-level queue scheduling algorithm. Fine. Now, why we need the multi-level queue? So you can see that as we go further, then we can easily classify our problems into different groups. For example, there is one common group is called the all the processes which is running in our system. All the processes can be divided in mainly two classes. The first one is called the foreground process. Foreground processes. And the second one is called the background processes. So these two are the two different classes of the process. Fine. So which processes are called the foreground processes? Those processes with which the user can interact, those set of processes are called foreground processes. But a set of processes which runs at the back, set of processes which execute at the background to complete the execution of the foreground processes, or to help the execution of the foreground processes, then those set of processes are called the background processes. So user usually interact with the foreground processes. So as the user is doing job through the help of some application interface, so definitely the user cannot wait for a long time. So we should execute the foreground processes faster or compared to the background process. That means the priority of the foreground processes is high compared to the priority of the background processes. Fine. So in case of multi-level queue, this ready queue. So if we divide the processes in two set of processes, foreground and background process, so in that case the ready queue will be divided into two sub queue. So consider this is my ready queue, or rather we can modify this one also. We can modify it, we can change it. We can, here there are three sub queues and we will convert it into one sub queue. Fine. So there is a single sub queue, two sub queue. One is the sub queue number 1 and sub queue number 2. One is used for the storing foreground processes and another is storing for background processes. Fine. So here you can see that for this particular example, the queue is divided into two sub queue. So let us say the first queue, queue number 1, is used to store the foreground process. And queue 2 is used to store background process. Fine. Now what happened? Again, that means the individual sub queue will work as a normal queue, normal ready queue. Fine. That means for each sub queue, a dedicated scheduling algorithm will be assigned. For example, for this foreground processes, for this sub queue number 1, let us say we will assign the FCFS scheduling algorithm. Right? So for the foreground processes in this sub queue, so all the processes which are associated with the foreground process, so all the processes will be stored over here, and those processes can be selected by the scheduler using the FCFS scheduling algorithm. Whereas the processes which are executed at the back end, they are stored over here, that means over at the sub queue 2. And let us say we will use the priority scheduling algorithm. Priority scheduling algorithm to execute or to schedule the processes, to select the processes from the background from the sub queue number 2. So here you can see on the same ready queue. So don't create a confusion. This entire thing is the queue and which is present over here. Basically, so this queue is divided, which is associated with the ready state, into two sub queue. The first one is used to store the foreground process and the second one is used to store the background process. Now previously only one scheduling algorithm is applied over here, but in this case we will apply two scheduling algorithms for two individual sub queue. So this is the advantage of the multi-level queue scheduling algorithm. And why this is advantageous? Because when the application will be open, that means the foreground processes will be open, definitely the user, whatever the process the user will open first, with that process the user wants to interact first. So based on that, so whatever the process the user will open, that process will be executed first. So FCFS will be a scheduling algorithm which is applicable for all the foreground processes. Now, in the background processes, we can apply the priority scheduling algorithm, or we also can apply the SJF algorithm. So, based on the selection of any one of the scheduling algorithm, the background processes will be selected from the sub queue 2 and it will be executed by the scheduler. Fine. So, now another very important thing you have to notice that between these two queue, it may be happen, that is one, this you can say it is a disadvantage of the multi-level queue, that between these two queues, from which queue, from queue number 1 or from queue number 2, from which queue the process will be selected first, whether the foreground process should be selected first or the background process selected first. That means again some selection strategy will be applied for the selection of the queue. That means first, if suppose this is in this example, there are two processes P1 and P2 which is stored in the foreground queue, and there is another set of processes P3, P4 is stored in the background queue. Now which subqueue will be entertained first, the subqueue number 1 or the subqueue number 2? That will depend on the classification of the problem. So let us say over here we will give the high priority of the foreground processes. So if this subqueue number 1 has any process, then that process should be executed first. And if the subqueue number 1 has more than one processes, then by using the FCFS scheduling algorithm, first the execution of all processes will be completed, then the process from the subqueue number 2 will be selected by using another scheduling algorithm, and the processes will be completed. Fine. So what I am saying over here, that in the subqueue number 1 there are two processes P1 and P2. So P1 will be executed first, then P2 will be executed first, and as after execution of the P1 and P2 no more process is present inside the subqueue 1, it is empty queue. So the process will be selected from the subqueue number 2, that is P3 will be selected, and then P4 will be selected for the execution. Or how the P3, P4 will be selected, that will depends on the scheduling algorithm. Now the thing is that if the situation is like this one, consider the example over here, there are two processes P1 and P2 in the foreground subqueue, and in the background subqueue there is another process P3. No other processes are present over here. Now what happened? So definitely as this subqueue 1 and the between these two subqueue number 1, that means the queue which holds the foreground processes will get the first priority. So P1 will execute first. Fine. Now during the execution of the P1, another process P3, P5 is inserted in the queue. So after P1, P2 will get the chance. Now while the P2 is executing, that means P1, P2 is not present over here, another process P4 is inserted over here. So after P2, P5 will be executed, then P4 will be executed, and so and so. So one after another, so a new process is inserted into the foreground queue. Fine. So the foreground queue is never become empty. The foreground queue is never becomes empty. So what will be the problem? No process from the background queue will be selected for the execution. So P3 will wait for indefinite period of time. So this is the major problem of the multi-level queue scheduling algorithm. Okay. So to solve this particular problem, we will go for the multi-level feedback queue scheduling algorithm. So in case of multi-level feedback queue scheduling algorithm, you can see over here, there is a feedback path from one queue to another queue. So those are the different queues. So let us say this is the queue which is this first queue is used to store the foreground process. The next queue is used to store the background process, and the last queue is used to store the interactive or rather say student processes. Fine. Now what will happen in the previously, what we see that in case of multi-level queue scheduling algorithm, if one queue is not empty, then that from the first queue which has the high priority, that first queue, the processes will be selected from that queue, and the processes which are present in the another queue will not get chance for the execution. So this is basically the queue scheduling algorithm, the multi-level queue is not so much flexible. So that's why this multi-level feedback queue has been designed. So here you can see there is a feedback path from one queue to another queue. So this is the feedback path. So there is a feedback path from foreground queue to background queue, or from background queue to student process. Fine. So suppose I should write it. It is better. So as per our previous example, we will write this last queue will be used to store the foreground process. This is used to store the background process, and this is a student process. Fine. So we will just change the existence of the process just for easy for understanding purpose. So let us say this is used to store the student process. This is used to store the background process, and this is used to store the foreground process. It will be easy for you to understand. Now, as we know that the foreground process will get the first chance for the execution. Fine. So here the processes which is stored in the foreground queue, those processes will be executed by the CPU first. Now the processes which are present in the student process queue or in the background queue, these two queue, they will wait. Now what will happen here? Some time quantum is assigned for each queue. That means time quantum values, let us say a time quantum value TQ equals to 8 milliseconds is assigned over here. Another time quantum value TQ is 16 milliseconds is assigned over here. So what will happen? And let us say that foreground process use FCFS scheduling algorithm for the execution. And those queues can use, suppose this queue can use the priority scheduling algorithm, and this queue can use the SJF scheduling algorithm. So different queues can use different scheduling algorithms. Now the thing is that as the foreground processes, and remember one thing, we have only one CPU. So whatever may be the number of queue, but one process can be executed by the CPU. So if the process is selected from the foreground queue first, then that process will get the chance for the execution. And if the foreground queue is already multiple processes are stored inside the foreground queue, so the processes which is present in the background and priority queue cannot get the chance for the execution. So what happened over here? There is a time quantum value TQ. So after that time quantum value, that means after 16 milliseconds, the process is present over here. If any process is present over here, it will wait for this time quantum unit. And if among this unit, within this time, if no process from this queue is selected, then some process will be transferred. One process will be transferred from the SJF queue to the foreground queue, so that the process will get the chance for the execution. The same is true for the priority queue also, this student process queue also. So here the processes are waiting, but if they don't get the chance for the execution, they will wait for a certain period of time, and after that the process will be shifted from this queue to this queue. That means the priority of the process, we will increasing the priority of the process. The execution priority of the processes are increased when the time quantum gets over. So when the time quantum gets over, that means 8 millisecond gets over, the process will be shifted from priority this student process queue to the background queue. Again, it will wait in the background queue. If it is fine, it can get the chance for the execution, it will execute. Otherwise, the process will be shifted to the foreground queue. So suppose here there are in this queue there is a process P1 and another process P2. There is a process P3 and here is a process P9. So first P1 and P2 will get the chance for the execution, and after completion of their execution, P3 will get chance for the execution. So while the P3 is executed, meanwhile P4 is another process is present over here. So after P3, P4 will execute, then after P4, P5 will execute, and so and so. So the processes from the background queues are executing one after another, and the process which is present in the student process queue is waiting for a long period of time. So what it will do, it will wait for this time quantum, and after that time quantum, the process P9 will be shifted, will be transferred from this sub queue to sub queue. That means P9 will be inserted over here. P1, that means the priority value of the P9 is increased, and P9 will now get the chance for the execution. So that is all about the multi-level feedback queue scheduling algorithm. So this is the overall scheduling algorithm. So far we learned there are the different scheduling algorithm. All the scheduling algorithm are classified into two categories. One is the preemptive scheduling, another is non-preemptive scheduling algorithm. And there are different scheduling algorithm we learned, that is first come first serve scheduling algorithm, shortest job first scheduling algorithm, shortest remaining time first scheduling algorithm, round robin scheduling algorithm, and priority scheduling algorithm. Apart from that, we also learned multi-level queue scheduling algorithm and multi-level feedback queue scheduling algorithm. So that is all about the scheduling algorithm. Fine. So that is all for today's lecture. Thank you for watching my video.